Okay, so now I'm in a position to write out how C cross section average is related to C bar using this fact. Sorry, how C cup mixing average is related to the cross section average, because I now have C tilde up to order P squared, right? So this is again something we did in the previous lecture. So Cm or rather let me write it in the following fashion. It will be easier this way. So Cm is simply U C by U. Right? This is the definition of the cross section average. So I can now write this as U. Remember, this is U tilde. By replacing C as C tilde, right? I get right, and this means cup mixing average is the cross section average because these terms cancel. So again, this is something I would have missed in the previous lecture by not having this denominator factor, but that's all right. So now I just have to evaluate this term. I know U tilde, of course, I mean, because I know the velocity field, and the C tilde I know up to second order. So I replace C tilde by C1 tilde plus C2 tilde, and then I multiply it by U tilde and take the average. So U tilde, of course, is just the U that I know minus this, right? So I can evaluate this from U tilde, subtract it out and get U tilde. I mean, yeah. And so so then I put that in and I evaluate this averaging operator and divide it by U bar, and the result was as follows. And this is of course up to order of P cube. So you see I have order P terms which involve this beta 1, I have order P square terms, and order P cube terms I have neglected here, where these various constants are given as follows. Beta 1 is 1 by 48, it's the same number you got in the previous lecture. Right? This term actually is intimately involved with the dispersion coefficient, whereas these new terms are different now. These are high order terms coming from the presence of possibly a second order reaction. Okay, so now this equation, right, which relates the cup mixing to the cross section average, arises only, I mean, basically it tells you the relation of these two, and these two averages are different only if you have variations in the cross section or imperfect radial mixing. And that lack of radial mixing, the corrections due to that are what appears in these terms coming from a perturbation treatment, and you have the corresponding constants here. Again, of course, if P is 0, you get the two to be equal, which will give you the PFR model. But now that P is non-zero, I have a correction, and this allows me to derive my corrected averaged model. Okay, so to obtain the corrected average model, I go back to the averaged equation which I had here, 3. I now know that the Cm can be related to the cross-section average C bar, but C tilde square I can replace using my perturbation solution, evaluate this average and see what I obtain. So then the final averaged model so let me call this equation 5. Looks like this. So now it's an ODE model, so I use the total derivative because Cm only depends on Z. I'll have no radial variations in this model because those have been averaged out, of course. So you see the cup mixing average is here and the cross section average is here, but I know the relation between these two using equation 5. And then I have 1 plus a correction arising for the case of second order or higher reaction rate kinetics. So if only there's second order or higher, this term survives. This is also only up to order p square, so order p cube terms have been neglected. Okay, so again here where gamma 1 has a value of 1 by 1440. This comes out if you do the calculation. Alright, so now 5 and 6. So 5 and 6 are my averaged model. Right, I need, of course, to solve this model now, I just need one initial condition, which is the cup mixing average at, sorry, why did I write Z here? It's X, my bad, X. So the cup mixing average at X equal to 0 is simply the cup mixing definition applied to the inlet concentration. This is strictly true if the inlet concentration is uniform across the cross section. If not, there are some corrections in the form of initial condition, which can also be derived by some refinements to this averaging procedure, but we shan't do that in this lecture right now. But it can be done. But if you have a uniform well mixed inlet solution entering which has no radial variations at the inlet, then this is exactly right. Okay, so the nice thing that we see now is that we have a complete model for describing a non-ideal reaction in a tubular reactor. If the Peclet is 0, like I said, or if you have a plug flow, you get back the plug flow model from here. Why? If Peclet is 0, Cm is cross-section average. Peclet is 0, you lose this correction and you just get the plug flow model. However, again, if you have first order kinetics, you lose these corrections, right? And you again get Cm is equal to C bar because this beta 1, which is 1 by 48, is true only for a parabolic flow. For a plug flow, so for a plug flow, beta 1 is equal to 0. Okay, so for a plug flow, you have beta 1 equal to 0 if you work out the calculation. So therefore, this term is lost. You still have a correction if you have sorry, so not only that, even beta 2 is 0. Yes. So even beta 2 will be 0. So basically, for a plug flow, both these beta 1 and beta 2 become 0, which is why you get again Cm is equal to C bar. But you will have corrections from here if you have nonlinear kinetics. For linear kinetics, you get back the plug flow model as we had anticipated. But anyway, in general, for nonlinear kinetics and non-zero Peclet, we now have a model accurate till order Peclet square that will allow us to correct for the effects of dispersion and the influence of the fact that you have the reaction rate occurring at concentrations different from the cross-section average across the radius. Or in other words, there are two sources of corrections here. One is the effect of axial dispersion that happens when you have imperfect radial mixing in a non-plug flow profile. This is something we saw in the previous lecture. We will see in a second how we can see the same phenomena from this model. But we know that this phenomena exists, right? So there is the phenomena of axial dispersion. In fact, that's what's been introduced as a non-ideality in your reaction engineering courses. In addition, you have another correction, which is basically shown here in these terms, right, which comes from the fact that the reaction rate is not the same across the cross section. Rather, at different positions in the concentrate of the cross section, you have different reaction rate speeds because the concentration is different. So the average of the reaction rates is not the same as the reaction rate evaluated at the cross section average. So that difference comes in these terms. So even this subtle effect, which you may not have thought of right at the beginning, it does come in naturally through the systematic averaging procedure. And you can always look at the model and understand where these effects are coming from later. Okay, so if one were to solve this problem, you can just solve this equation using standard ODE solvers, although it's a differential algebraic equation. So what needs to be done is you use this equation 6 to advance Cm, but in the next time step from that value of Cm, you have to calculate C cross section average by solving equation 5. Typically this is some kind of, it could be a nonlinear equation. Yeah, in general it's a nonlinear equation. And then so you solve this using some kind of root solving method to calculate C cross section average for a given value of Cm, plug it in here to get the right hand side of the ODE, and then advance along the length of the reactor. So there are many, if you just implement this in MATLAB or Mathematica, you can easily solve this DAE, differential algebraic model in only one spatial direction. But it's considerably simpler to solve, of course, than the original PDE, where you would have to discretize in R and X. Okay, so we shall see a numerical comparison of this model to a full PDE calculation in a second. Before that, let me finally look at axial dispersion from this model. Okay, so remember in the previous lecture we derived something similar to this model, and what we then did was we substituted C bar in terms of Cm or vice versa into the right hand side term, and we got an effective single equation which had a effective diffusion term. So you will get d square by dx square times the coefficient, which is what we interpreted as the dispersion coefficient. We can do the same thing here, although it requires some more algebraic manipulations. I shan't go into that. Instead, I'll just give you the final result. So I can also write, you can substitute 5 into 6 and ultimately obtain, with some manipulation, an equation of the following form. So, sorry. Is equal to, so I'll get an effective dispersion coefficient. I'm writing it here in terms of the cup mixing average, plus, minus times some terms involving the reaction corrections. Okay, I won't write that out, it's not important here. But basically it involves, I mean, you will have all of these terms coming in here. Okay, all of this stuff comes in here. And this as well. But the main point is, you can rewrite this reaction rate term back in terms of convection and operate the derivative, and you will get this term. Okay, so without going into details, the main point is the effective dispersion coefficient here in this problem with a reaction in dimensional form. I'm just giving you the final result here, is the Taylor dispersion coefficient, right? This has the factor beta 1 in it. Inside, right, this Taylor dispersion coefficient is what we derived in the previous lecture. So the effective dispersion coefficient I get in this problem is the previous lecture's Taylor dispersion coefficient, right, with the correction factor, that is the radius squared upon the molecular diffusion times beta 1 minus beta 2 by beta 1, sorry, it's a plus sign. times R prime of Cn. Okay, so the main point I want to make here is that this term indicates that the reaction affects laminar dispersion. And we can calculate what that effect is exactly by using this averaging procedure. So this is a deep physical insight and an important one. Why? Because typically when we model non-ideal reactors, what we do is we do the RTD study, right? So in a presumable non-ideal plug flow reactor or a tubular reactor, laminar tubular reactor, we carry out a residence time distribution study where you put in, let's say, a plug of solute and you observe the outlet concentration, and from that you try and calculate. If you fit the result to Taylor's dispersion model, you can empirically get a Taylor dispersion coefficient. And then we use that dispersion coefficient inside an axial dispersion model of the form I've written on the screen, something that looks like this. Now those models are wrong for two reasons. One is that the reaction rate, you would just have minus Darmkuhler number, reaction rate evaluated at the cross-section average, forgetting about these reaction corrections. So our average model gives you those corrections. Secondly, the dispersion coefficient you use in those models are typically the same you obtain from RTD under cold flow settings or in the absence of a reaction. But what we're seeing here from our derivation is that that effective dispersion coefficient is actually different in the presence of a reaction. Why? Because the radial concentration variations are affected by that presence of a reaction, as it wouldn't be if you did not have a reaction. So even though you can use a Taylor dispersion model or the use of a dispersion type axial dispersion model for a non-ideal plug flow reactor is valid, that is what this average equation seems to suggest. However, the dispersion coefficient you use there cannot be the same as that in the absence of a reaction. So you need to account for that correction. Or in other words, you should do an RTD study with the reaction occurring, not without the reaction. And also you have other corrections coming from the fact that the reaction rate applied at the average concentration is not the average of the true spatially varying reaction rates. So I think that's another important point. So still mostly people use RTD data in the absence of reaction to size reactors and to use it in the presence of reaction, which is strictly incorrect as seen here, but it's often hard to do these experiments under reaction rate settings, and it's not easy to obtain models that give you that correction. But what we're seeing, or what this lecture shows, is that if you use systematic averaging along with perturbation methods, you can actually derive these results in a rigorous systematic manner. And more importantly, it shows you these physical effects just like this one, where the reaction affects a laminar dispersion, which can then serve as important indications for what to expect when you actually look at either simulations or experiments of these phenomena. Okay, so the last thing that we look at before concluding this lecture is to actually see a comparison between the predictions of this model and the solution of the full PD equation 1 to see how well this model works and whether it actually gives us a better prediction than the plug flow model. So that's what I've done. Sorry, that's exactly what I've done here. So you see that I've actually solved the same problem we just looked at in our derivation. I've taken the Pectet number to be 100, which is of course much larger than 1. This is just to show you how well this model works. So in our derivation, we assumed small Pectet and order 1 Darmkuhler. Here I've taken 0.1 Darmkuhler and a Pectet of 100, which seems to be out of the range of validity of our derivation. Nevertheless, even for this large Pectet number, you will see the model works well. That's the point I wanted to make. So under these parameters and second order reaction rate kinetics, I solved the full model, the full PDE model, and I also solved our averaged model. So the result of the full PDE model is the blue line, the averaged model is the red dashed line, and the PFR is the black dotted line. And I'm plotting the concentration here in the reactor as a function of the reactor distance, and you can see it decreases because the reaction is consuming the solute. And the important thing to note is you can see how the average model gives you a much better prediction than the plug flow reactor model, even if the Pectin number is quite large. So this is often true in perturbation methods where you assume certain orders for different parameters to do the perturbation method systematically. But when you actually go and compare results, you find quite often a pleasant surprise where the model works quite well even for relatively large values of the perturbation parameter. So the other point is now you can see the difference, especially later down as you go towards the outlet of the reactor. You can see that of course the reaction length is scaled here, so you can see that the average model gives you a far better prediction than the plug flow reactor. The vertical distance may not seem much in terms of the scale concentration, but let's say you want to calculate the point where the let's say you want to calculate the length of the reactor, that you need to get 80% conversion, which means you will want the concentration to go from 1 to 0.2. Then you can see that there's a sizable difference. In one case, the true result is a reactor length of about 45 units, non-dimensional units. So, but your PFR will give you a much shorter reactor, right? So, if you use a PFR, you will get much less conversion than you expected, which in terms of scale conversion may be only less than a point, but less than 0.1 difference. But in terms of product in a continuous flow reactor operating for days, you will lose a huge amounts of product, and that even small percentages of difference can make a huge difference in your output. So you can see that you get a much better prediction on the length of the reactor from this average model than the PFR model. And however, you should, while at the same time noting that the computational cost of solving the average model is not much more than the PFR model, right? The PFR is an ordinary differential equation model. The average is a differential algebraic but also ODE model. It only depends on the x direction, just like the PFR model. So the computational increase in computational cost in using the average model over the PFR model is minimal, but it's much less than the computational cost of the numerical full PD model. At the same time, its predictions are almost as good as using the full PD model. So this is really the power of averaging and perturbation method.